In this session we're going to focus on regression. Before talking about regression though, I want to talk about a really important concept when we think about statistics, and that's the difference between statistical significance and really practical or substantive significance. It's possible, and we'll look at an example in a little bit, to have a model where we find statistical significance, but practically speaking the effect is pretty small. And it's important to inspect both of these and to make an interpretation that is really informed by both of those. So the statistic that we use to think about substantive significance in regression is the coefficient of determination. This is simply r squared. It's the square of the Pearson correlation coefficient r that we talked about before. What's interesting about the r squared is you can think of it as the proportion of variation of one variable that's due to change in another variable. So for example, if you're looking at a bivariate relationship and you have an r squared of, for example, 0.6, then you can say that 60% of the variation of one variable is related to variation of the other variable. So we'll use this in a little bit, but first let me talk a bit more about regression analysis. So regression analysis builds on the concept of correlation, but it goes beyond it, because with regression we can not only look at the strength of relationships, we can also make predictions. So for example, we can find out what factors predict rent, and then we could actually make some estimates on what rent could be charged based on certain levels of those different factors. In terms of the data, we're going to use interval or ratio dependent measures such as apartment rent and one or more interval or ratio IVs, or independent variables. So for example, we could look at rent as a function of distance from campus, as a function of ratings of the apartment decor, etc. But these are all variables that are measured on scales such as 1 to 7, 0 to 100, and so forth. Assumptions that we make include that the variables come from normal populations, and the error terms, which we won't really focus on in this session, we assume that they're normally and independently distributed. So here's our conceptual model for apartment rent. And as far as regression analysis, it would be appropriate to look at monthly rent because that is a metric variable. Specifically, this is a ratio variable because it has a natural 0 point. We're not going to use likelihood of choosing the same place again as a DV because that's a categorical variable. So we could look at monthly rent as a function of one or more of these variables. If we looked at the relationship between one of these IVs and monthly rent, that would be a bivariate regression. If we looked at more than one IV and their effects on the DV, that would be a multivariate regression. So regression builds on simple ideas from mathematics, where any unique line can be defined by two variables. One is the slope, and the slope basically says for given unit change in the x-axis, what is the effect in the y-axis. In this case we have a positive slope, but of course we could have a negative slope as well. But we also need to know the intercept. In other words, if this variable were at the level 0, if the rating of interior decor design were at 0, what would rent be? Mathematically, here's what it looks like. There's our intercept. We'll call that a constant in regression. And then we have our B coefficients. In this case, it's a bivariate regression, but you could have multiple B's in here. So this is simply reminding us that with multiple regression, we're looking at the effect of multiple predictors on a single dependent variable. So let's take an example. We're going to look at apartment rent in Williamsburg, and we're going to predict that using our data based on the average ratings of interior design decor. That was one construct we created, and we also created another construct for rating of the neighborhood. We want to know if rent is predicted by one or both of these other variables. Here's what that would look like mathematically. And let's say that we ran through the data and found a model like this. And let's assume for a second that all of these numbers are statistically significant. This would be A, or what we'll refer to as our constant, and then this is the B coefficient for decor and the B coefficient for neighborhood. And the way we'd use this to predict rent, if for example we had an apartment and we knew that the decor was rated a 3 on a scale of 1 to 7 and neighborhood rated a 4 on a scale of 1 to 7, we'd simply put those numbers in here, 3 into decor, 4 into neighborhood, and we could compute that the rent would be most likely somewhere around 700. I say somewhere around 700 because this formula would suggest 700, but we know that there are probably other factors that come into play as well. But that's how we actually use the coefficients that we get from regression analysis to make specific predictions. So let's go ahead and look at a couple of examples. So since we've been talking about rent and decor and neighborhood, let's go ahead and see if those factors are significant predictors. And I'm going to go to regression, linear. The dependent measure here once again is rent, and my independent measures are decor and neighborhood. I'm going to select OK, and we'll see what we find. Now the first thing you want to do with a regression analysis, and it's important to do this first, is see if the overall model is statistically significant. There's no point in interpreting the specific coefficients or making any other statements if the model is not significant. Now we've done a regression analysis, but note here it says ANOVA. That's simply because ANOVA regression or actually one is a subset of the other, so technically this is correct, but we have run a regression analysis, and this box is where we're going to get our F statistic. Note that it says that our overall model is not statistically significant. Our F of 1.3 exceeds our threshold of 0.10. There's no point in inspecting the specific coefficients. We'll go ahead and do that anyway just to show you that neither of these coefficients is statistically significant. But we would have known that just by looking at this. Our model is not statistically significant. So, at least according to this data, within Williamsburg, neither rent is not predicted by either neighborhood ratings or ratings of decor. So let's try another model. Again, you analyze regression, linear. I'm going to reset to take those other variables out. Put back. So let's try another model. Again, you analyze regression, linear. I'm going to reset to take those other variables out. Put back in rent. And now I'm going to see if rent can be predicted by the number of bedrooms and or the number of bathrooms. Click OK. And once again I'm going to start with the F statistic. Now, in this case, the F of 3.8 is statistically significant at less than 0.05. So that means that we do have a statistically significant model. But is it practically significant? And for that we want to look at the R squared. And this is a judgment call, but it's important to inspect the R squared to make some determination based on that. Now there are two different values that we're looking at here related to R squared. Well, actually there's the R value, but we can simply square that and look at 0.055, and then there's an adjusted R squared. I'll come back to that in a second. With R squared, what this says is that only 6% of the variance in rent is due to the number of bedrooms and the number of bathrooms. So that's actually a relatively small percentage. So it's statistically significant, but we have to be careful using this. If you were to use this in a business case, for example, you would want to know that most of the variance in your rent is unaccounted for. So you'd want to be careful about making predictions. Now adjusted R squared is related to R squared. You'll notice it's a little bit different. Think of adjusted R squared as the same as r squared, but with the small penalty for every additional variable that we put into the model. Because otherwise, all things being equal, the more variables you put into a model, even if they're not statistically significant on their own, usually are going to increase the r squared. So what the adjusted r squared is doing is accounting for that. So it's penalizing us for the fact that we have 2 predictors instead of 1. So we've looked at the statistical significance, we've looked at the substantive significance. Now let's go ahead and inspect the coefficients. And there are 2 different sets of coefficients here. The first thing I'm going to do is look for the significance. What this says is that, first of all, our constant, and this is important, our constant of $872 is statistically significant. So that means that any use of these coefficients to predict rent need to include that y-intercept or constant in the equation. Of our 2 variables, only Bath is statistically significant at p less than 0.05. So we have 2 different sets of coefficients here. We have these unstandardized coefficients, and we have these standardized coefficients, also called beta coefficients. We'll call these B coefficients, and these are beta coefficients. And they're used for different purposes. If you want to predict rent, then you want to use the unstandardized B coefficients. So let's say, for example, we want to understand what would most likely happen to rent if we added in another bathroom. Let's say we were thinking about renovating a bathroom and we wanted to get a sense of how much more we could charge per month. What this says is that for every unit change in bathroom or addition of 1 bathroom, we could charge on average another $225 per month. So that's how we use the B coefficient for predicting our DV. So what's the purpose of the beta coefficient? Well, let's go back to how these were actually measured. These were measured on a similar scale in a sense, because the number could be 1 theoretically to infinity. But we're just asking about numbers, number of bedrooms, number of bathrooms. But imagine for a second if we had 2 different types of variables. What if we add in here the square footage for an apartment, in square feet obviously, and then we had distance to campus, which would be in miles. We'd be looking at 2 variables with very, very different scales. So we'd still want to use, in that case, the B coefficients to make predictions about rent, if they were both statistically significant. But how do we determine which of these 2 variables is actually the stronger predictor? Since they're on different scales, you can't really compare these numbers. And that's where the standardized coefficients come in. Essentially, what SPSS is doing is it's looking at the data and transforming it so that each of these variables has a mean of 0 and a standard deviation of 1. You don't need to worry too much about that. Only know that it's standardized the data, so now these are comparable. So what that means is I can look at these 2 numbers right here, and assuming that they are both significant, and they are not statistically significant, but imagine for a second that they are, then I could make determination about which one has greater explanatory power, which is the more powerful of the 2 variables. It would basically be which of these 2 had a larger beta coefficient.